We're talking about buoyancy, and that could be spelled completely wrong. Nobody knows how to spell buoyancy. It's one of the facts of physics. Buoyancy, if you've ever been in like a lake or an ocean or a pool or something, you know, you can like pick up your friend. They're pretty light when they're in the water. As soon as you like, you know, do a press over your head with them, they turn just as heavy as always. But if we look at a pool of water real quick, we've already talked about how we know that the gauge pressure beneath some liquid is equal to rho g h, the density of the liquid, local gravity, and then the depth you are beneath the surface of that liquid as well. Well, if I put a box, it's like we always like to use nice boxes, in the liquid, then from the surface down to the top of the box, this has some initial height 1, and from the surface down to the bottom of the box, this is some height 2. And as we've talked about in class already, we know that since pressure is rho gh, that change of pressure is equal to rho g delta h. Well, if the pressures at the top and bottom of the box are different, that means that the top of the box is experiencing a force, F1, that is less than on the bottom of the box because there's more pressure down there, and pressure acts in all directions. So the reason why things feel lighter is because if we look at F1 and F2, well, a force is equal to a pressure over an area, and that's the top of our box there. That's, you know, this lovely area right there. And since we know what pressure equals, this will be rho g h1 times some area. As for the lower part of the box, or F2, same equation, P2, the pressure at the bottom, times some cross-sectional area. That equals rho g h2, the lower depth, times that cross-sectional area. Now, what we start to realize, and we talked about this whenever we worked out the initial pressure equation, is that, hey, look, if you have a density and a height combined with an area, what you really have here is a density times a volume times g. And this here, this is the volume of the object, which means that that's the volume of the liquid that is being displaced. And this is the density of the liquid. Well, if that volume of the object is equal to the volume of the liquid displaced, well, the volume of the liquid displaced times the density of the liquid gives us the mass of the liquid that's displaced times gravity. Well, mg, we think of that as a weight, but really it's a force. And what that represents there is the buoyant force. This buoyant force is the difference in force. It is F2 minus F1. Okay? Because what we're really thinking about here is we're thinking about doing rho g h2 minus h1, which is what this height of the box is right here, h2 minus h1 times a. And that gives us our mass times gravity for the weight, and that's our buoyant force. So that's what we're looking at here for a buoyant force, and that's what gives us some sort of liftoff here. So the question rather becomes, if you have a floating object or whatnot, if we start thinking about this buoyant force, how much liquid are we displacing, and what are we displacing it with? So maybe that gives you a better idea for that ice problem, Haluko. But that's kind of the idea of buoyancy right there. And we'll talk about more of that tomorrow. I know the other class got a little bit ahead today. So, but that's buoyancy, a quick little nutshell for you.